Hello and good afternoon, and thank you for attending this talk. I'll be going over the topic of influence of ester on the mechanical hysteresis characteristics of power transformer insulation components. My name is Daniel Braga, I come from INEGI, and this work was conducted by INEGI and EFACEC Energia. In this presentation, I'll be going over the problem statements, listing the problem that we intend to solve. Then I'll go over the experimental methodology that we have employed, show some of the results that we have obtained so far, and then finish with the conclusions and the next steps in this ongoing investigation. So as you are, I'm sure that you are aware, power transformers are a critical component in our modern lives, as they are a critical piece of equipment in our electric power grids. They are, however, subjected to very significant loads, namely when a short circuit occurs, as it goes through very dynamic loading conditions. Inside these power transformers, we have a dielectric and cooling medium, so a fluid, which in the majority of situations nowadays, it is used mineral oil. Mineral oil works very well for this situation. It has been doing so for many years. However, it is non-biodegradable. It is synthesized from fossil fuel resources and is toxic. So if we want to go forward to a more environmentally conscious equipment and more eco-efficient, it would be a good starting point to come up with an alternative to this dielectric and cooling fluid. And one such alternative that may occur is the natural or synthetic ester, which may be plant-based, biodegradable, and is naturally synthesized, as well as non-toxic. Besides the environmental concern, there's also the point of view of safety, namely fire safety. Since mineral oil has a much lower flash point than natural ester, when we are employing a power transformer to a dense populated location, or even in a sensitive location, as we are aware there were this year a lot of fires in Europe and as well in the United States, California and so on. Electric equipments might be an important concern going forward in the point of view of fire safety. So by employing natural ester, since it has much higher flash points, we will also be having much safer equipment to operate in high temperatures. And as well, there's the point of view of efficiency of the transformer, since the materials when embedded in natural ester have a higher thermal class, which increases the maximum operating temperature and improves the eco-efficiency of the power transformer. So for this study, in order to study the mechanical performance of important components in the power transformer, namely the insulators, when impregnated with different fluids, we have studied a series of materials in different conditions to evaluate and compare their mechanical performance. Two classes of material were studied. One was extra hard pressboard insulators, and the other one was metaramide insulators, namely Nomex. Two different thicknesses were used for the pressboard, so 2.5 and 4 millimeter thickness, nominal thickness, as well as different aging conditions were used. So all of these materials were either in a new condition, so with a fresh set of dielectric fluid, or aged. The aging process was done by immersing the insulators in the fluid at an elevated temperature to accelerate the aging process, and the degree of polymerization was measured. The degree of polymerization went from 1500 to 1700 to about 400 or 500, and we have to take into consideration that if it reaches 250 to 300, it is considered end of life for the fluid in a power transformer. The specimens that were used to test were stacks of either 3 or 5 60mm discs, which was depending on the nominal thickness of the specimens. So these specimens were then tested according to IEC 60641/2 standard in in-house developed testing machine. This test consists on loading in three stages. It's a compressive study where during the compression of the material we do see some of the fluid expelling out. So this standard involves doing the three-step loading, as I was mentioning, where first we have an initial loading, which equates more or less to 1 megapascal. Then it's compressed at a constant rate until it reaches another loading, close to 40 megapascals, and this will equate to a specimen height of H0 and then H1, and then at the end, when decompressing to the same load level as in H0, we'll have the H2. And through these calculations, we can have the compressibility, in percentage of strain, let's say, the residual part of that compressibility, so the non-reversible, and the reversible part of that compressibility. Beyond the stated in the IEC standard, we can also look in these tests at the compressive and then decompressive stiffness, which is what was shown here in this calculation, and it is marked in the graphs in this black line. So the first metric that you can look at is the compressibility, which is the difference in specimen height during this compression test. And we can see that there is no significant difference between different mediums and aging condition, only being observed differences between the materials. So the pressboard materials have higher values of compressibility than the metaramide insulators. Regarding the reversible and residual part of compressibility, we can indeed see some differences between the mediums, the materials, and the aging condition. One of the first ones that we can observe is a difference between aging and non-aged mineral oil, where we can see that there is a reduction in the residual part of the compressibility. We can also see that this reduction is more prominent in pressboard than it is in the Nomex material. The point in the case of ester, we see less significance of the aging condition. In the case of Nomex, and ester, we see a slight increase in the residual part of compressibility when the material is aged. Regarding the compressive and decompressive stiffness, we can see that there is no significant difference between aging and between the mediums, but we can see the influence of the materials itself in this property. As we can see, the pressboards have generally lower stiffness than Nomex material, and there is a higher difference between compressive and decompressive stiffness in the case of pressboard than in the case of Nomex. The differences in compressive and decompressive stiffness is here more prominently shown, where we can see that indeed pressboard does have higher differences in between these two, while the metaramide material Nomex has no smaller stiffness difference. So to conclude, we can state that it is indeed important to look at materials to replace mineral oil in power transformers, and that it is important to know the mechanical performance of these materials in these mediums. What we observed during this experimental campaign was that the metaramide based insulators have indeed lower compressibility than the extra hard pressboard insulators. That the metaramide based insulators are stiffer and maintain their stiffness better when decompressing. that the cooling and the electric fluid had no significant effect on compressibility nor in stiffness, and that the aging of mineral oil reduces residual compressibility, particularly in pressboard, while the ester does not. So as for next steps, we need to also look at the different mechanical performance in different environment conditions, namely in terms of temperature. So we are developing equipment to test at -40, 120 degrees and 190. For -40 we'll use a Peltier-based solution, and for the other temperatures we'll use a convection chamber. We also require to study the performance in high strain condition due to the cases of short circuit loads, as I mentioned before. And we'll be doing that in a special made electromechanical machine, again at the different temperatures, operating temperatures. To end, I just want to thank the funding for this study, and I'm available for any inquiry.